So, basic radiation theory all starts with this problem, the Hertzian dipole. What is the Hertzian dipole? Well, let's say we have the origin. Here's our problem. We got an origin, and I've got some point of observation in spherical coordinates, distance, elevation, and azimuth. So I've got a radiator at the origin, and I want to know what is the electromagnetic field at that point of observation. Hopefully it looks like a spherical wave at that point, and it will have a pattern around it. That pattern will depend on what we put at the origin. The simplest thing that we can put in the origin is a tiny infinitesimal current of I, measured in amps, existing exactly at the origin. And in fact, we have to give it a little bit of physical length, otherwise it won't radiate anything. So we give it a little element dl. Infinitesimally small with respect to a wavelength. You could even collapse it as a delta function with respect to z if you wanted to. But this is a z-oriented current. So let's put the z-axis up like this. X would be here, Y would be into the board like that. And we have a tiny little element of current whose charges are going back and forth and back and forth and back and forth and back and forth. That's the simplest radiating system we can possibly conceive of. Now let me sketch out the incredibly ugly solution to this equation, so that you can at least appreciate what your electromagnetic colleagues have to go through to study these fundamental problems. My H-field phasor, as a function of r, theta, and phi, my point of observation, that's going to be given by j I dl, my little length, times my current amplitude. This is sinusoidal current at a frequency. So it does have a frequency dependence that's actually wrapped up in the wave number, which recall has units of radians per meter. It's just 2 pi over the wavelength of radiation. Sine of theta, so depending on the elevation angle, this amplitude changes, divided by 4 pi r, 1 over r attenuation of fields, exp minus jkr. And this is going to be multiplied by, I've got to figure out a way to do this because it's going to take 2 board rectangles. So I'll just write it and then I'll jump back and forth for the viewers at home to do my explanation. This is how I'm going to write it. Let me just write the whole solution out here and then we'll go back and talk about it. Electric field as a function of point of observation equal to j I dl. Eta, my impedance of the medium, sine theta 4 pi r exp minus jkr times theta hat minus j hat plus 2 cotangent theta r hat over kr minus theta hat plus 2 cotangent theta r hat. Okay. Now, let's see if we can. Oh, good. Okay, that'll work. Let's start on this one. We'll start here. This is, keep in mind, the simplest radiation system that we could possibly think of. This is the exact solution. I've got 1 over r attenuation of both fields. In fact, everything propagates just like the spherical waves that we talked about last class period. exp to the minus jkr is a linear phase taper. In the phase domain, when I convert that back to the time domain, that's a traveling wave that moves away from the origin at a constant velocity. 2 pi over lambda is the wave number. I get some angular dependence here. Here's sine theta in both terms. In fact, these are identical terms, except they differ only by that impedance function. That makes sense, right? Or that impedance constant. This is magnetic field in amps per meter. I need something to multiply by impedance to get volts per meter. And impedance is the natural ratio of E and H that a medium transports, such as free space. Then we get into these polarization terms. Look at H for a second. I have a phi hat. So that means that my oscillating current is going like this, and my H field is, at least that component of it, is swirling around in phi hat, my azimuth unit vector. Down here, theta hat, E field, I have my oscillating current back and forth at the origin, and the E field is oscillating back and forth. It's a phasor, and it's oriented in the theta hat direction. Okay. But there are extra terms, of course. So now let's jump over to this board. And look what we have here. There's also, and actually this should be yeah, that was right. Never mind. Here I've got a phi hat term and another theta hat term and an r hat term, and both of these are divided by kr. So when I do this particular grouping, I've grouped it in a particular way such that these are your order kind of kr to the -1 terms. On the previous board, we all had kr to the -0 terms in the brackets. This is kr to the -1 term. Okay. And over here, there's nothing in H, but you see down here in E, I've got kr to the -2 terms. So I got a theta hat and an r hat component. So this is order kr to the -2 terms. Okay, now why have I grouped things in this particular manner? Well, when kr, let's step back and even ask a better question. How do I use antennas? Do I use them to communicate from here to here? Or do I use them to communicate from here to space, or to a base station antenna, or to a wireless network access point? We're usually going many, many wavelengths in distance. Now recall that my kr, k of course is 2 pi over lambda. When you multiply it by r, when this term is less than 1, kr is less than 1, I'm going to be getting a large number. These terms that I've drawn on this board are going to basically dominate. They're going to be the big ones, and they're going to drown out the little theta hat and the little phi hat order kr to the 0 terms that I've got on the board. These guys over here. These are going to be drowned out. And if that's the case, then if I look here, r is less than lambda over 2 pi. In fact, if I want to be really conservative, these terms I'm going to have to take into account in radiation whenever r is less than lambda. And we call this part of the near field of radiation. In fact, I like to be a little bit more specific, and most EM professors are like this. We call this region the quasi-static region. of an antenna. And what's happening here is that the reason why we call it a quasi-static is because if you think of a little line of current, if it wasn't oscillating, it would still have a magnetic field around it. It wouldn't be sending any traveling waves out like this antenna would. But if it was just a DC magnetic field, it would still have, it would still be like a magnetic dipole moment that fell off as a function of 1 over r to the third. Or it would also be an electrostatic dipole as well, because you'd have charges building up on one end and depleting on other as the current went back and forth, oscillating the polarity. That would also be an electric dipole moment, and sure enough, that field would also fall off very quickly. And you basically get a lot of energy that is stored in the field around the oscillator, the oscillating current. It's not transporting any power. It's really just sloshing it back and forth as it's stored in the immediate area of the antenna. Immediately in the area of the antenna, it's these terms that dominate. When I get past here, this point, for this particular antenna, I'm in the far field, this little oscillating current. And then I can pay attention only to these terms over here. And my goodness, that's pretty much where we always use antennas. In fact, most of the time, we're so many gajillion wavelengths away from the antenna that we can neglect these things altogether without any loss of contact. We can't even measure the difference if that's the case. And so in this class, this is how we treat radiation. This fields are only falling off 1 over r, so they last a lot longer in amplitude as you move away from the origin. And this is what's transporting your power. In a nice TEM wave, transverse electromagnetic wave, the components E and H are in phase, 90 degrees polarized from each other, transporting power away from the little radiating Hertzian dipole out into the deepest of space. This is an important example to study. I didn't take the time to derive where this came from. We do that in our undergraduate antennas class, and I'm sure the graduate antennas class. But there are some important takeaways for you all here. First of all, you'll see the term far field come up again. In fact, I've got an extra qualification for far field when we move into sizable antennas. But it's important to recognize that there's a lot going on in an antenna. We're only interested in the far field transmission of waves. The other thing to recognize is that by describing this Hertzian dipole, we have now, with this little solution, the building block of any antenna. Because really, at the end of the day, what is an antenna? It's a collection of currents sloshing up and down on metal. To figure out how those currents radiate, all we have to do is treat that as a collection of Hertzian dipoles. Each chunk of that antenna is like a Hertzian dipole with a particular amplitude and a particular phase. If we can estimate how the current sets itself up on an antenna, then we can figure out how that turns into a radiated field and basically figure out what the pattern is of that antenna by synthesizing and superimposing all of these solutions on top of each other. Did you have a question? You have a comment? Why did I approximate the equation? Okay, so when R is greater than lambda, then that means that KR is much less than 1. And so these are, think of these as my order KR0 terms. So they don't even depend on KR. So they're always going to remain constant in magnitude. Relative to this term and this term, these other terms, because they depend on KR to the -1 and KR to the -2, get very small, and I neglect them. relative to these terms. So I just get rid of them. And I'm left with that simplified expression. So now, because I'm always operating antennas in the far field anyway, I'm going to build up those I can use that Hertzian dipole to build up more complicated antennas. Before I do that, though, this is a really nice simple antenna that I can use to define the principal characteristics that we're going to use to characterize an antenna. For example, first of all, I need to figure out power, right? I've got field quantities here. I want to turn it into power. So let's take the pointing vector again. The average pointing vector, which tells me the average number of watts per meter squared radiating out of a system, we said was 1/2 the real value of E phasor vector crossed into H phasor vector complex conjugate. I've got an expression now for the far field of E and H, so I'm going to write what it comes out to be when I do all the math here. I get I squared dl squared k squared sine squared theta, and of course an eta. And that's going to be in the r hat direction, power carried away from the origin. In the denominator, I've got a 32 pi squared and an r squared. Okay, so that's the power carried away from the origin. Notice it falls off 1 over r squared. That makes sense. That's good that it worked out that way. And then over here, the only angular dependence is this sine squared theta term. It means my little Hertzian dipole radiates, first of all, there's no dependence on phi. That makes sense. It's a radially symmetric problem no matter how I look at it. It does have a dependence on elevation. There's a null at theta equals to 0, which would be right along the z-axis, and also theta equals to 180 degrees, which is negative z-axis. It's at a maximum down at the horizon along the xy plane, the way that I've oriented this problem. So that's how the power flows. So again, we're getting there. We're in watts per meter squared in terms of our units, but I'm still got these geometrical field theory quantities like current and dl. What I really want is a gain pattern. So the first thing I have to do is figure out how much total power am I actually radiating in this system. Well, I can calculate this very easily by bringing back some bad memories for some of you, by invoking some vector calculus, right? My total power in this radiated system should be the pointing vector dotted by a surface normal integrated over a closed surface. I'm going to choose the surface of a sphere. So what I'm going to do is I'm going to integrate over the area of a surface of a sphere, picking up all of the pointing vector contributions sticking out of it. So what is that going to look like? So I'm going to integrate from 0 to 2 pi along azimuth, and then from 0 to pi in elevation. And that'll get me all 4 pi steradians of a sphere. What is my element of integration going to be here? Well, if I cheat and I look at the back of the calculus book, it's going to be r squared sine theta d theta d phi. That's how I integrate on the surface of a sphere at a given distance r from that sphere. So now I just plug this into here, dot it, and keep in mind this is a vector. I need a surface normal pointing out from that sphere to do this integration. And of course, what is the unit vector that always points perpendicular to the surface of a sphere? It's r hat. Okay, so that makes it actually easy because r hat dot with r hat is 1. I have a nice scalar thing in my integrand from here on out. I've got a sine cube term, theta. That's the hardest part of the whole integration, but that's easy to look up in the back of the calculus book. Let me just write the answer without browbeating you with the mathematics. When I plug this into here, I get pi I squared dl squared eta over 3 lambda squared. Yeah. And this should be power of watts. Okay. So now I have total power. How do we calculate gain in that case? Well, we said gain is always with respect to an isotropic radiator. If we know how much the total power of this system is, this little oscillating current is radiating this much power. If I took that power and I isotropically radiated it, it would basically be PT over 4 pi r squared. And so we're going to define a term. It's not going to be gain yet. I'll explain the difference in a second. But in antenna engineering, there's a term called directivity, which is the precursor for defining gain. It's a function of theta and phi. And it is, by definition, your radiated power, which we called SAV, with respect to your isotropic power. So I take this power that I found, the total power here, I plug it into here. I've got an expression for my average pointing vector up there on the other board as well. When I'm finished, this is what I get. Missing the sheet. Oh, here it is. Here we go. It's actually very simple. I don't even need the formula sheet. If I did this normalization correctly, I should get 3/2 sine squared theta. That's really all I'm doing. I'm normalizing the radiation against its average isotropic power. If I integrate this number, the directivity, over 4 pi steradians, I should get 4 pi. Or if I average it over 4 pi radians, I should get 1. That's a better way of saying it conceptually. And so, in most instances, this is going to be a little bit greater than 1 in some regions of space and less than 1 in other regions of space. And we see that. Along theta equals to 90 degrees, when this sine term becomes 1, that's anywhere along the horizon, then this value is 3/2. I'm getting 50% more than isotropic radiator. When I get up into theta equals 0 or theta equals 180, then I go down to 0. I'm getting much less than an isotropic radiator. Overall, it all averages about to be the same. Now, you'll notice that I called this directivity. I haven't called this gain yet. Gain in a radiating system is equal to directivity times efficiency, where efficiency is always less than 1. Efficiency tells you how much of your power that you sent into the antenna is actually making it into radiated modes. So the gain is always less than the directivity. If it's a good antenna, it's not much less, but it's always going to be less than the directivity. Where do you lose power in a radiating system, whether it's being used as a receiver or as a transmitter? Well, ohmic losses, for one. Your antenna is not usually made out of superconductor metal. So when it sloshes current back up and down, there's a little bit of ohmic loss there. If you make it out of copper, silver or gold or some really nice piece of metal, or you're just operating at low frequencies and you don't have much ohmic loss, you're usually okay. Then that number is relatively low. Whereas some other sources of loss, dielectric loss, if there's any plastic or even the air around the antenna, if the frequency is high enough, will impart dielectric losses to your radiation and will be included in this term. In fact, there's a big debate often in antenna engineering about whether you should include mismatch losses. So, for example, your antenna, as we're going to show in a second, has an impedance. Impedance is measured in ohms, but it's not ohmic losses. It's really the transport impedance of the antenna, the ratio of voltage to current that it naturally accepts electromagnetic power from. So if an antenna has a certain impedance, well, so does the line that feeds it. You have a transmission line leading up to that antenna. That transmission line also has a natural impedance. If it's not the same as the antenna, then a portion of that signal will reflect back to establish the proper boundary conditions to allow voltage and current to be continuous across the boundary from the transmission line to the antenna. Reflections generally are bad because they mean that you're not sending all of your power into the transmit antenna, or you're not receiving all of the power that you could from your receive antenna into your receiver. It's reciprocal. It works both ways. So if you have a 50 ohm line, you should have a 50 ohm antenna. If not, you get a matching problem on your hands, and you have to make some special, you have to put a balun or a matching circuit of some sort in between them. Usually satellite engineers don't worry about that level of detail. The antenna engineer has probably figured all of that for you. The antenna that you spec out is usually given its parameters matched to one of the standard transmission line feeds, for example, 50 ohms. You say, well, at 50 ohms, this is the, they've got some matching circuit in there already, and they basically tell you what the gain is with respect to 50 ohms. So keep in mind, sometimes your gain that you pick off of the spec sheet not only has radiation efficiency, but it may also have mismatch losses mixed in there as well. Technically, that is called realized gain. This is called absolute gain if it's directivity times efficiency without the mismatch losses. There's a standardizing body in IEEE that comes up with all these terms. I sit on the IEEE nerd committee that comes up with these for wave propagation in antennas. This is always like an endless source of confusion. Technically, absolute gain is this. Realized gain is when you include mismatch. And more often than not, spec sheets, well, they call it gain, but they're really talking about realized gain. So just keep that in mind when you go to practice as an engineer. Realized gain also includes mismatch losses. We won't worry about mismatches in this class. You can always assume it's a realized gain that I'm giving you unless I specify otherwise in a problem statement. For your project, you'll probably have to spec out some antennas for your class project. And so just be on the lookout for the difference between realized gain and absolute gain. Recognize that if you pull a value off a spec sheet, it probably includes any mismatches relative to 50 ohms or whatever they're measuring their antenna with respect to. Okay, any questions about that? Okay. So this is the directivity of the Hertzian dipole. If I have a very efficient antenna, it's pretty close to the gain of the Hertzian dipole, too. So once again, in this class, unless I tell you otherwise, assume that you have a really good antenna. And if I give you a gain directivity, unless I tell you otherwise and give you an efficiency, you can approximate your gain as that directivity. Now, I mentioned the idea of an impedance. This still is kind of important because you need to know electrically how to interface your circuit to an antenna. So hopefully you'll be able to know whether or not this thing needs a matching circuit or not. And it turns out we actually have enough information to calculate what the radiation resistance is in this antenna, what it will look like in a circuit. So you can imagine we have a transmission line. It's connected to the Hertzian dipole. What will this thing look like in a circuit? Well, I'll tell you what it looks like. In a circuit, it will look like a resistance. And this resistance we call the radiation resistance. And in a circuit, it looks like an ohmic loss resistor. But really what it's doing is taking real energy out of my transmission line system and putting it into radiated modes. Yeah.
Yeah, sorry. It's about the power transmitted formula. So when we integrate the pointing vector, it's at a fixed radius.
Yeah, that's right.
So why don't we have the radius in the final equation?
Why don't you have a r in a final equation? Oh, so it's at a fixed radius, so I've got an r squared here, but then in here I've got a 1 over r squared, so they always cancel out. That's right. And that makes sense, right? If we're in a lossless medium that doesn't have any absorption of power, then it doesn't matter how big I make the sphere. As I make the sphere larger, if I double the radius, the surface area goes up by a factor of 4, but the energy density goes down by a factor of 4. So it always averages out. And I always get the same constant regardless of my radial point of observation. It's a good observation to make. And since I know that, let's say I have a current I going into here. Well, what is that current? It's the same current that's going to be radiating on the antenna, I. 1/2 I squared R, rad, my radiation resistance, is going to be my total transmit power. It should be I squared. I squared R is my radiated power. I've got to put a 1/2 because these are sinusoids. And I have an expression for total power radiated. This is going to be pi, I squared, dl squared, eta 3 lambda squared. I squareds cancel, and I find my radiation resistance is going to be 2 pi eta over 3 dl lambda squared. So isn't that interesting? I know how this thing is pretty much going to behave in a circuit just based on how the current, how much radiation the current is sending out into the environment. If I have an I that's radiating like this as a Hertzian dipole, I got to feed it with that current with a transmission line. And notice I've done something here. I haven't connected my circuit yet because I'm only dealing with real power. There's also going to be a C, a very, very large C, because this is a highly capacitive system, because it's not a resonant. I'd actually need to get a real value impedance for a pure radiator like this. I actually have to get this thing to stretch out in space to at least a half a wavelength, right? Got to have a half-wave dipole. When I have electrically small radiating structures that are lines of current, they wind up being very capacitive. And this is why you don't use tiny, tiny antennas with respect to wavelength, not if you want to actually receive something. You have to give it some electromagnetic length, and that makes the C go away and the radiation resistance go up. What is the radiation resistance for the Hertzian dipole? Well, it depends on the length with respect to wavelength. We said this is really only valid when dl is a tiny infinitesimal, much, much smaller than a lambda. So I've got 377 pi over 3. In engineer speak, that's 1 times 2. So I have some numbers, probably like 700 times this ratio squared. So if this is 1/100th of a wavelength and I square it, it's like 1/1000. I get a radiation resistance less than 1 ohm. this is a problem. The problem isn't that it's not a good radiator. The problem is that it's almost impossible to couple a significant amount of power from your transmission line, which has a natural impedance of 50 ohms or 75 ohms or whatever you've made it out of. It's hard to couple that into the antenna. Most of the energy reflects at this junction. And that's true when you use the antenna in reception as well. It has the exact same impedance as at reception. And most of the power bounces right off of it. You can't couple it into the receiver because it's so badly mismatched. You say, well, wait a second. So I've got a very small R and a huge capacitance. Any electrical engineer who's taken circuits knows that you can resonate some of that reactance out of the network and then do some sort of impedance transformation. And those games work well when you're kind of mismatched. But when you're severely mismatched, the first thing you have to do is get rid of this C, the capacitance. Well, that means you need an inductor, right? So I start winding a coil of inductance. What's the problem with inductors? They tend to be relatively low Q, right? The more inductance you accumulate, the more series resistance you accumulate as well. So even if I could get rid of this capacitance with an inductor, I'm going to leave a little bit of resistance in the circuit pathway, which will wind up being much larger than my radiation resistance. And so there's only so much I can do to get rid of that capacitance. And that's just one of the many travails of matching these types of antennas. So you'll find the only place that I can use electrically small antennas is in the field of, say, low-frequency communications, where my first free space path loss is so low anyway, I can take lots of lumps when my antenna losses and still do communications. So it doesn't matter that the frequency or the wavelength of AM radio is over tens of meters long. I just take a little wire, I whip it out there. Yeah, I'm losing 20, 30, 40 dB in inefficiencies, but the first free space equation is so forgiving down at AM frequencies, it doesn't matter. Likewise, the most extreme example of this is in submarine communications. You've probably seen like the movies where you send a signal to a submarine that's deep beneath the ocean, right? Well, the problem is we can only propagate really low frequency signals into salt water. Salt water is a very unforgiving radio wave environment. We're talking like kilohertz or less. And so how do you get a signal from the United States to, say, a nuclear submarine that tells them to surface or take some course of action that's very important for national security? Well, you got to transmit at these very low frequency ranges. And in this case, the wavelength is hundreds of kilometers down at that frequency regime. So how do you even make an antenna? Well, there was even talk of using like an iron ore range that went across the Midwest and pumping power into that and using that as like a dipole. It would be long enough with respect to frequency where you could actually legitimately couple power into it. Instead, I think they just lay a cable across Minnesota or something to do this now. And then you want to send the signal to the submarine. The submarine's going to have to just take its lumps. Right? You just throw out a cable, hope it gets enough length and signal to receive your low-frequency communications. You can only communicate very slowly. You've seen them in Hollywood movies, right? The little boop, 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 boop. The little letters come off the communication device very slowly. So surface and get the real message. So that's the most extreme case, when your lambda is so large and your antennas, no matter how big you make them, are relatively small. They all act like Hertzian dipoles in a way. Okay, any questions so far? So we've defined a couple of key parameters in antennas. We've talked about the directivity. We've talked about its relationship to gain, which is what we use in our link budget equation. We also talked about impedance, just because it's good to know that parameter to make sure that you're matched with whatever transmission line you're feeding it. And there are a couple other things that you should probably know about antennas. Once you've calculated the directivity, or the gain, there's a nice parameter that we often see on spec sheets called the half-power beam width. Let me put a couple common parameters that you'll see. First of all is peak gain. What is the peak gain? In this system, it is 1.5. It occurs at theta equals to 90 degrees. If the dipole is oriented along the z-axis, that's along the horizon. More often than not, though, you'll see this number reported in dBs. That'll be about 1.8 dBi. The half-power beam width, or sometimes called the 3 dB beam width, of an antenna is how far you can go to the left and to the right of the peak gain and still get within 3 dB or 1/2 of the power transmitted by this antenna. So in the case of 3/2 sine squared theta, we need to solve for the half power points in theta, which can give me up to half the peak gain. Peak gain is 3/2. Half the peak gain is 3/4. And we find for this particular academic example, theta is either going to be 45 degrees or 135 degrees, pi over 4 or 3 pi over 4. So the half-power beam width for this antenna is the difference between the two, or 90 degrees. If I look at this antenna, directivity, and I slice it, so here's Z, and here's X, Y going into the board. This is a 3D radiation pattern, and it makes effectively a donut. It is independent of azimuth, but there is a sine squared theta with respect to elevation. So if I took a slice of the pattern, I would see like a 2 dumbbell shapes. Nulls in the vertical direction, peak gains here. The half-power beam width would be 90 degrees. I would go to this point or this point, and that would get half the power. In other words, most of the power is being transmitted by this antenna falls within these sectors here of 90-degree width. So yeah, that is also a very helpful set of parameters for antenna engineers. Okay. Any questions so far? Well, that is the basic Hertzian dipole and the fundamental quantities of antenna engineering that we just covered. Half-power beam width, peak gain, impedance, directivity, radiation efficiency. No matter how complicated an antenna gets, those capture almost all of the interesting behaviors that we use to engineer and talk about them. And so what we'll do on Thursday when we come back is we'll start talking about electromagnetically larger antennas. And we'll come up with an equation that relates the shape of the current, and hence the antenna, to the radiation pattern. I won't derive it in detail, but it's a really important result to understand because it helps us pin down a little more tightly what the far field is of an antenna. And it also gives us an intuitive understanding of how to relate radiation pattern to the shape of an antenna, to the point where you can actually look at an antenna and say, oh yeah, that's clearly a good satellite antenna because it's got a very pencil-thin radiation beam in every direction. Or you say, oh, yeah, that's a good cellular antenna. It's clearly sectorized here and has a lot of gain along the horizon where all the paying customers are. Oh, that's a good radar antenna. It's very wide in this direction and narrow in this direction. I know that's going to send a pencil thin beam that captures all of the elevation angles I need to track aircraft.